Hey, good morning. We got people here already. Let's see. Oh, it doesn't like my white sweater. It's like glitching out. There we go. How is everyone this morning?
Good.
It's good.
Come here, baby.
Hey. Oh, look at this little. Oh my gosh. Oh, geez. I would get my cats, but they're in like sleep mode in another room. Yeah, it's interesting. The color does not like my light sweater. Interesting. What's the dog's name?
It's Tank.
Tank. Seems appropriate. Yep.
She won't be here the whole time.
Oh, it's all good. It's funny. I have in my office here, I have a door and there's like French doors, but the cats will sometimes want to get in. So they're like meowing to get in, and then you let them in. And then you shut the door because they want the door quiet. And then they meow like to get out. And I'm like, make up your mind. So hopefully they won't bother me. Yeah. So Allie, you had a new job over the last few weeks, right? Is that still
Yeah. I lost my job at a cafe
right?
and I had to be able to pay the bills. So
Gotta do it.
I'm working seasonally as a stalker at Aldi.
Mm-hmm.
The hours are unpredictable and pretty much every day conflict with class time, but today I somehow got off.
Hey, well, I'm glad to see you. It's nice. Yeah, I know everybody's schedule's been in upheaval for sure. So I feel like every day I feel like I'm just saying, I'm just trying to limp through to the finish here. Like we're just trying to make it through at this point. Survival. Yeah, we've been ordering from Aldi a lot actually.
Yeah, are you using Instacart?
Mm-hmm.
We love our Instacart shoppers.
Yeah, I mean, I feel a little bad. I mean, it's good, but I feel like I'm trading my risk for their risk. You know, like, but so we just tip big. Like, I appreciate you shopping for us. So here's a tip for risking your health to be out shopping for us.
Yeah.
We're doing the same thing. We tip all of our food shoppers I have to
Yeah.
get fresh produce all the time because I make the baby's food from scratch.
Ah,
So I'm
right,
constantly having deliveries and everything picking up. And I'm like, I'm so sorry, guys, but thank you.
right, right. Yep. We bought some Visa cards and we leave them for the Amazon delivery people sometimes. Little extra thank you. I should have reminded people that we were meeting on Monday. Maybe I'll do a quick post here. Oh,
I had to literally set it on my calendar because I figured I was going to totally space it today. I'm
Yep,
not used to having Mondays off. So it's kind of like, wait, what?
yep. I don't know if a news item will work. Maybe I should email everybody. Maybe that would be better. I'm just gonna do a quick email. Class list. Well, we're getting more people here. Getting some of the usual gang showing up. We got Juan here. Good morning. Good morning, JT and Haley. I didn't say good morning to Sandra either. Let's see. We're going to do a quick email to remind everybody that we are on this morning. Let's see. I love how I have my phone number in my signature as if I'm checking my phone. Like that's my office phone. Like, no, sorry, don't call that.
I brought another dog.
Another one, just as cute as the other one.
There are 4 of them. It's
Oh my
overwhelming.
gosh. Oh, I'm gonna have to go get a cat then. That's it. I'll be back. Hold on. Okay. hold on. We're going to click. I'm going to just email everybody here a quick reminder because some of our usual suspects are not here today. So I'm like, maybe they forgot. Okay, hold on. I'm going to get a cat. Do you want gray cat or diluted calico? What's your choice?
Gray cat.
Gray. Okay, I know where she is, so that's good.
Bring your pet to
Chantel, you'll love this. These dogs are addicted to coffee. They like coffee. Mickey, you want some? No, he's not in the mood right now. Look. No.
Right now I've got the baby in the walker and she's chasing the dog around the living room and the dog's freaking out because now she's mobile. So right now mine is like hiding on the couch, trying to avoid her at all costs.
That's funny. Yeah, I feel bad for the dog that we had when I was a little kid. I was not nice to him.
Well, that was supposed to be my son's dog, and that didn't turn out right.
I don't think I can get I can't get the headphones on with her. But anyway, this is Athena.
Oh, nice. Yeah, every time people see him, they ask if he's a cat or a dog.
He's like, what are you doing? What are you doing? Let me out. Let me out. And she's off. Okay. She's like, really? Really? You got me up for that? All right. Oh, Albert's here. Good morning, Albert. Anybody else?
Morning.
Good morning. Man, oh, we got another dog. This dog is a lap dog. Yep, lap dog. It's a 60-pound lap dog.
Not a lap dog. Doesn't understand he's not a lap dog. But now he's seeing all the other pets on the screen.
So he's like, come on, where's my moment of fame?
Yeah.
I need my... All right. I guess today we have a quiz to go over. We'll talk a little bit about the exam, do some requests. I did want to thank everyone who filled out the survey. There's some like super thoughtful, whoa, maybe I need brighter lights. Super thoughtful comments there. So I appreciate that. So please, if you haven't yet, please fill out that form. It's just kind of questions about what worked this semester and what didn't, and suggestions in case I'm planning for an online class in the fall too. So there's been some really thoughtful comments there. So today we're going to go over the quiz, talk about the final, like what to expect. I do have a draft pretty much ready to go. I do want to try it to make sure it doesn't take me like an hour and a half or something. That would be way too long. So I usually try, like for a final, I want it to last a couple of hours. So I usually would want to be able to finish it in like 40 minutes or something. So I have to go through it yet today, but that's pretty much ready to go. So we could talk about that. And then we'll do we can prioritize earlier review if you want. We have a few more 5.5 examples still to do. We could do that. Our last class meeting is tomorrow. And so we're just going to focus on review tomorrow. And then the exam will be released immediately after class. And then it'll be due Wednesday at midnight. So, any questions about schedule? Any schedule questions? Ooh, let me get the chat up here too. Anybody have any questions about the plan? All right, I thought I would go over the quiz first, so let me pull that up. All right, so number one here, this one is this like weird theoretical fundamental theorem of calculus part 1, which just says, if you have an integral of a function of t dt, and you're integrating that from some number to x, and you take the derivative with respect to x, you just get f of x. That's what the fundamental theorem of calculus says. And it's kind of weird here, but if you have a function of t and you're integrating from a to x. So you have this area, which is a function of x. As x slides back and forth, the area increases or decreases. And if you want to know how fast that area is increasing, it's just the function value at x. It's just the function value at x. So all you have to do is just change the t to an x. That's the practical part of it, but it seems like just a little game, but there is a theoretical foundation for it, and that's the fundamental theorem of calculus part 1. For number 2, you're just going to find the antiderivative of these functions, and then evaluate them at the upper limit and subtract evaluating them at the lower limit. That's the more practical fundamental theorem of calculus. That's part 2. So 1 over x cubed is x to the negative third. Add 1 to the exponent, that's negative 2, and divide by negative 2, and evaluate that from 1 to 3. So you get 4/9 if you do that. For letter B, the antiderivative of 1 is x, because the derivative of x is 1. And then the antiderivative of secant squared is tangent. And again, you evaluate those at power over 4 and subtract evaluating those at 0. All right, any questions on the first couple so far? All right, not seeing any questions. All right, on to the second page. This one is, we talked about this is a really important concept. So you know when I mentioned that, we talked about it, we kind of knew there was going to be a question here. I'm mentioning it again, that's really important. I'll let you infer from that what you want to infer from that. So what does an integral mean? So a definite integral, we talked about introducing it as area under a curve, but if our function represents a rate of change, the integral represents the total change. So W is the rate of how fast the water is being added. It's kiloliters per hour. It's a rate of change of the volume of water. So the integral is the total change in water, total change in the amount of water. In our case, it's measured in kiloliters because you have kiloliters per hour. If you ever are wondering about those units, you could literally take, this is kiloliters per hour times dt, t is in hours, times hours gets you kiloliters. You can do like unit analysis if you want. And then so it's the total change in the amount of water, and specifically over those 36 hours, because it's from 0 to whatever 0 is, but 0 to 36. So the definite integral is total change. That's the key here. All right, number 4, last one here, average value, just a formula. I think I mentioned this already, but you can have a formula sheet. There's a lot of formulas. It's hard to remember all of them. So you can have that for the final. So this is one that you should just have written down, this average value of a function. Basically, it's kind of like the same as average. You add them all up and divide by how many there are. So the integral adds all the function values up, and you divide by the length of the interval. So it's 1 over 4, that's the length of the interval is 4, and then you integrate from 0 to 4. The only issues I saw here were some people just kind of forgot to integrate, and they just did the square root of x from 0 to 4. But you have to integrate x, you add 1 to the exponent 3/2 and divide by 3/2, and after you simplify, you end up with 4/3. This is posted on D2L, so you can welcome to take a look at it there as well. Any questions about the quiz? All right, I'm going to move on. If you need that, it's under Unit 5. It should be like way at the end. There it is, Quiz 11 key. So at the very end, there is a Quiz 11 key. You can see. I think I linked it. Yeah, I linked it on the homepage too. You should see feedback to yours in the Dropbox as well. So next, I kind of want to just leave it up to you. We'll talk about the final, about what to expect, but also like after that, we can do more 5-5 examples if you have specific requests, or we could kind of do some review from earlier things. So let me talk about the final. one of the things I always tell my students is the final should really be like big picture. What is the point of the course? That's the exercise I went through when I wrote the final. I'm like, okay, what are the big ideas? Limits, derivatives, and then integrals. And so within that, what are the main ideas within that that you need to be able to do? Like, we found these indeterminate limits that were 0 over 0, right? We talked about that a lot. We talked about the tangent line a lot. Rates of change. Derivative means a rate of change. We talked about that a lot. We talked about the graphs, increasing, decreasing, concavity. All these things we talked a lot about. Those are the big ideas of the course. These antiderivatives and integrals at the end, right? Just doing an integral and what it means. So my point is, when you're studying, you really should be starting with your old exams, because that's stuff that I thought was important during that chapter. And if it was important during that chapter, it's an important idea. So if there's some little topic that we talked about in class and maybe was on a homework question, but we never tested it before and it was never on a quiz, it's not going to be on the final. If it wasn't important enough to include on a quiz and an exam, then it's not important enough to be on the final. The final is like big picture stuff. So I would, number one, definitely, hopefully you've been working on this already, but I would, number one, focus on the old exams and be looking through your old exams, which is why I posted them. They are all under, there is a final exam materials folder here. And there's all old exams, old study guides, and then video YouTube keys if you want to look through those again. And that's a lot. You're not going to be able to look at all that tonight. So you might have to focus on things that you have questions on and things like that. But you want to focus on some of those exams, because that's the stuff that I thought was important before. Albert, you had a question. Go ahead.
I remember you saying something about Newton's method not really as important. So
Yeah,
I'm
I think
guessing would it be on the test?
No, we can leave out Newton's method. Some of the other stuff, like the derivative definition, is useful, but it's not some. Now I'm more interested in, can you use the derivative? So that's another one. Those were two that I was thinking of yesterday when I was doing the exam. So the one thing I do want to mention about chapter 5, that we did not have a unit exam on chapter 5. So I want to make sure that you understand the idea of area as a definite integral and approximating it with lower and upper sums. That idea is going to be really important in Calc 2. So that's going to be there. Of course, all these antiderivatives and definite integrals like we had on the exam, and integration by substitution, fundamental theorem of calculus. We want to make sure that you know all of those things. So those will all be on the final. Chapter 5 will have something from each section pretty much on the final. The earlier chapters, it's going to be like little snippets. Though I will say, like if I ask you, where is a function increasing or decreasing, I'm also testing, do you know the derivatives of those functions, which might have been like 2 different sections earlier in the semester. So I kind of cover multiple sections in one when you have like a broad question like that. So a lot of it's kind of cumulative by nature, but chapter 5 is, we haven't had a test on that. So we're going to kind of prioritize each of those sections. Yeah, you want to make, I see your hand, Elliot. You want to make a formula sheet as well. There's a lot of stuff. So I want you to make a formula sheet. You can have a whole page. And I just will ask you to include that with your exam when you upload it. Go ahead, Allie.
Oh yeah. Are we gonna need to do Newton's method at all?
No, that's the one that Albert was just wondering about. And that one's kind of
I missed that.
It's okay. It's a useful skill, but not something we're going to do on the test. So good question. All right. Any other questions? Kind of, we're not doing like review yet, but just kind of specific questions, Chantel? Clarification question?
Yeah, no, I'm just, like when we go back to section 1, when we had it algebraically, like as the limit of h approaches infinity or as h approaches c, are we going to solve that algebraically, or are we going to able to use the cheats where we can use like the quotient rule, the power rule, and stuff like
Yes. So
like unit 1 was very much trying to show the explanation. So is it going to be like worded like it was in unit 1?
Yeah, so I think what you're thinking of is like if we want to find, I don't know if we called it the derivative, but if we want to find the slope of the tangent line at C, we could do a couple of different definitions, right? We could do the limit as x approaches C, f of x minus f of C all over x minus C, or we could do the limit, did we do h or delta x? I can't remember. Did h? H goes to 0, f of C plus h minus f of C all over h. So yeah, so what I think what we're going to focus on is we're going to focus more on, we will have limits like we might have a limit that looks like this, but not phrasing it like this. Like we might have some limits. They might look like that, but they're not necessarily finding the limit of a slope of a tangent line. So all the ones that are finding the derivative, finding the slope of the tangent line, we're going to be able to use our derivative rules for those. Yeah, so let me pull up an exam, see if we can see what Chantel's talking about, because I remember what you're talking about. But just so everybody else, well, hold on, they're right up here. I don't need to open them. That's why I put them here. So exam 1, chapter 1. So let's see if we can find the one that she's talking about. Limits. So here's what I'm talking about, like number 3. You see how this is, there's limits here? So you might still have limits like this. These are just limits. You might still have these limits. So here is the one that Chantel was talking about. Find the limit as x approaches C of the average rate of change. Right, so the key is that that's just the derivative, and now we know how to find the derivative, and so we can just use our derivative rules at this point to find that. I feel like there's another one too. Maybe not. Nope. I think that's the one. Good. Any other questions about what you should expect on the final? I've got the chat up too if you want to type there. I was trying to like wear a sweater today, but now it's like, I don't know if you can hear that. He's hitting the zipper. Go ahead, Albert.
Sorry, for the formula sheet, does that include, I don't know, this is probably stupid. Does that include like antiderivatives and derivatives?
You can include some of that if you want.
Okay.
It's okay.
I don't know if that was in a formula or not, or just
yeah, right. It's like, So I guess it's kind of, I shouldn't call it a formula sheet. Like you can basically write whatever you want on your sheet, one sheet. Okay.
All right, sounds good.
Yeah. I am going to ask, by the way, I have the final drafted. I am going to ask something a little bit different at the beginning. So single page formula sheet. Here's your stuff you can use. I'm going to ask you to write a statement and then sign this at the top too, just kind of stating like, yep, I've only used this stuff and I did all the work myself, and just kind of sign your name there at the top. I haven't done that before, but that was suggested to me to somebody, kind of remind people that, you know, we can't be texting our friends for help on this, and we're only using this stuff here. So that'll be a little bit different on the final. I know you want me to scroll down. I'm not going to, sorry. All right, this is good to kind of clarify. Any additional requests or questions, kind of clarifying questions about what to know, what you should be studying, what you can do? Okay. I guess my next thing on my list today was maybe let's finish some 5.5 examples. So why don't we do that next? I have those examples that are posted in D2L under Unit 5, way at the bottom. There's 5.5 examples, and you can they're not too hard to write down. You can just write them down as we go here. But we did most of them on Thursday. And so we just have a few left that I think it would be good extra practice. I mentioned this before, but this integration by substitution, this technique is pretty much ubiquitous throughout Calc 2. So I know your Calc 2 instructors in the fall will understand that you got this at the end and it's a crazy semester and they'll do some review for you, but I still want to make sure that you're as prepared as possible with this strategy. So let's do a few more. I think we just have one indefinite left. That's number 5. And then I think we have a bunch with bounds left. 9. Yeah, we have 2 more that are definite integrals. We have 2 more of those. So let's do example 5 here. Remember, with the substitution is you're literally doing a substitution. You're picking a u. Do you remember another time in the course where we picked a u? Way earlier in the semester.
That'd be the chain rule.
Yeah, chain rule, right? So this feels like the chain rule. And in fact, it is. It's the reverse chain rule. Integration by substitution is undoing the chain rule. That's exactly what it is. So it should feel like the chain rule where you have one function inside another. So we have u equals 4x. We do the differential du. That's just the derivative 4, but then we have a dx from the x there. You'll notice in the integral, this one's actually set up nicely. It's secant squared of 4x, and I'm just going to reorder it and put the 4 with the dx. They don't always line up nicely like that, but this one does. So this then becomes, after we substitute secant squared u du. And then we have a much simpler integral after we do that substitution. And that's one that you probably know. If you don't, Albert's point, you want to make sure to have these written down. Does anyone remember that one? Secant squared? What's the antiderivative of that?
It's a tangent.
Yep, right, Albert, tangent. That's the tangent of u. And don't forget our plus c, like I forgot on the last exam when I did the antiderivatives. You want to have that plus c there. And then we just have to do our substitute back in. So tangent of 4x plus c. And so that's the antiderivative. And one nice thing we talked about this, you can actually check your work. When you get to the final, you've got extra time, you can check your work. Someone remind us, how can we check our work when we do an antiderivative or an indefinite integral like this?
You take the derivative of the antiderivative.
Right. And we should get, hopefully when we're done, 4 secant squared of 4x. So we can take the derivative, tangent of 4x plus c. So this is a chain rule. What a coincidence. It's because it's the whole point of substitution is it's the opposite of, it's undoing a chain rule. So that's secant squared of 4x, but then we need a chain rule. The derivative of 4x is 4, and then the derivative of c is 0, and then you look, that's what we had. Secant squared of 4x times 4. So it checks. So you can do that on any antiderivative. Any antiderivative, you can check that. All right, let's do some definite integrals. We have 2 left here. And I'm going to do these the way that I like to do them. It is not the only way to do them. Sometimes, as instructors, we kind of have to make some choices. And if you show every way to do it, it can almost end up being more confusing. So that's why I do it. I kind of just pick one way and try to be consistent with that. So I'll do the substitution, u equals x squared plus 1. I'll do my du, 2x dx. I don't quite have that. All I have is x dx. So I'm going to divide by 2 and call this 1/2 du equals x dx. So that's pretty good. I have u squared times 1/2 du. Right, the u is x squared plus 1, so that becomes u squared, and then x dx is 1/2 du. And then one thing that I like to do is that the 0 to 1, those are x values. But now I'm integrating u. So I like to do and evaluate, like think of u as a function. U evaluated at 0 is 0 squared plus 1, which is 1. And u evaluated at 1 is 1 squared plus 1, which is 2. And so now my integral in terms of u goes from 1 to 2. So now my integral is entirely in terms of u, and the benefit of that is now I can kind of like reset and just pretend I started there. X is gone, no more x. We're not going back to x. We just have a new integral. So this is 1/2, and then u cubed over 3 from 1 to 2, which will be 1/6 times 2 cubed minus 1 cubed, which is 1/6 times 8 minus 1, and so that's 7/6. So I didn't need to go back to x because this equality here between the first integral and after I did the substitution, that's true. That first integral is equal to that second integral in terms of u, so I don't need to go back. That's it. I can just keep going. Any questions at all about that example 9 there?
Sorry, where did the 1/6 come from?
Are you okay at the step where I have 1/2 u cubed over 3?
Yeah, I'm trying to figure out from there.
Yeah. So
it's like,
it's just 1/2 and then times 1/3, right? So
okay.
like, just kind of saying 1/2 times u cubed over 3 is the same as 1/2 times 1/3 times u cubed, and then I can just try to treat it as 1/6.
Yeah, I was double checking. Like, did you multiply 1/2 times like 1/3 or something? Like,
Yeah. Yep. So I like to always put that coefficient out in, like even if it's a denominator, kind of put it out in front as a coefficient. It just seems easier to me. All right, any additional questions? All right, I think we just have one last one here. Integral from 0 to 2, 3x squared times the square root of x cubed plus 1. So again, just kind of like chain rule, we're going to let u be the inside part here. So that's x cubed plus 1. du is, oh, this is nice. It's already set up for us here, 3x squared dx. Who is Jigna? I don't know who this is. That's not good. I see. Thank you. It's like I get nervous when I see a name. I'm like, wait a minute, who is that? Who is that name? All right. Okay, so we have 3x squared. We're already set up here. This one's kind of nice. We have the integral of, we're going to have square root of u, and then 3x squared dx is du. And then just like for the previous one, I'm going to redo the bounds. So u, thinking of u as a function, u at 0 is 0 cubed plus 1, which is 1. And u at 2 is 2 cubed plus 1, which would be 9. So 1 to 9. And I like to do roots as exponents, u to the 1/2 du. That'll be u to the 3/2 divided by 3/2 from 1 to 9. I don't know about you, I don't like to divide by fractions. I'd rather write it as a multiply. So divide by 3/2 is the same as multiplying by 2/3. Then I'll have 9 to the 3/2 minus 1 to the 3/2. And then you can do a calculator for this, but you don't really need to. That's square root of 9 cubed minus 1 to any power is 1. Square root of 9 is 3. 3 cubed is 27. And so we would have 50. Oh, nope, we can do better than that. 3 goes into 27 9 times, so we get 18. And I want to show you what what this integral is representing again. I did this exercise the other day. Let me just show you what the substitution is actually telling you. So we have, we'll call it y1 equals, it was 3x squared times the square root of x cubed plus 1. And we were integrating that from 0 to 2. We need to change our scale here. Oh, even more than that. Wow. Okay. 50. And we're going to graph this just from, actually we could do this. We could say we're going to graph 0 less than or equal to y1 less than or equal to from 0 to 2. What? That is not working. That's what it is. Sorry, I'm having Desmos issues. Okay, so that's the shaded area underneath the original function. And what's interesting is we actually made a y2 function, which was just the square root of u, we'll call it square root of x. And we shaded the area underneath that one from 1 to 9. And so crazy enough, the blue area, the area under the original curve from 0 to 2, I don't think it can, like, Desmos is smart enough to actually shade the area. So it can't like tell you what that area is, but that area is the same as the purple area. So we kind of converted this function to this function, and they give the same area. You can kind of see that they look the same. It's hard to know exactly just from looking at it, but they look pretty similar. And so that's the point of substitution, is it makes your complex function into a similar function, but you have to change the bounds to get the same area. If you went from 0 to 2, you wouldn't get the same area. You have to change the bounds so they match the new function. And that's integration by substitution. Now, I'd like to have every single integral involve substitution, because that's the most important part on your exam here, but it's just one section. So we'll have some that don't involve substitution, but we'll definitely have a couple, probably at least one definite integral where you have to change the bounds, and probably a couple of other ones as well. But then we'll have some that just normal antiderivative or general indefinite integral, no substitution. But again, prepping you for those going on to Calc 2, pretty much every integral you do there will involve some kind of substitution. So it's a very, very important skill to be confident with. So any last questions on these last couple of substitution examples? Okay, I have homework up. We could do that. I also have the Unit 5 study guide, which I posted, which is pretty long. But if you wanted some extra examples, I should get myself a blank copy ready. So we could do homework questions if you want. We could go over that study guide. I have the homework up here from 5.5. So why don't you? And sometimes I feel like it's kind of whoever's first. So you can use the chat too. You can even message me privately if you want, or you can just type in the chat. So I'm going to get the study guide up, but if you in the meantime want to just unmute yourself and say something, or if you want to type in the chat a request, feel free to do that.
Can we go over homework question, please?
Yeah, do you have a specific one, Sandra?
31 from 5.5.
Okay, 31 from 5.5, sounds good. Just going to get this study guide up here. I don't know what I would do if I only had one screen. This monitor, my second monitor, is really old, but it seems to work fine. Like I bought it with I used to play online poker back in the day before I had kids and before online poker was illegal. And I bought my monitor with some of my winnings so I could play like 6 hands at once. That was fun. You had to stay up until like really early in the morning because that's when all the college kids would come on who thought they were good but were not good at math. So it's like 10 years old. It still works, but it's nice to be able to have the two. Like I don't know what I would do if I didn't have 2 monitors. So you said 31, Sandra? All right. Let's pull that one up. This is a nice example. This is actually like a pretty typical difficulty level for this. It's not super easy, but it's not crazy hard either. It just, to me, it looks intimidating. But you'll notice the e to the function. So there's a function inside the exponential function. For me, that's like red flag. Boom, chain rule, or in integration, of course, it'd be substitution. So we're going to let u be equal to 1 over x. For derivatives, I like to write it as x to the -1 because I'm going to find the differential du. I want to take the derivative, so I like to use the negative exponents instead. So that will be negative x to the -2 dx. And now for my substitution, I'm actually going to rewrite this as -1 over x squared dx, just so I can recognize it in the original function. And you'll see I'm close. I have 1 over x squared dx, but we have this extra negative. So I'm just going to multiply both sides by -1 and call it negative du equals 1 over x squared dx. So that is negative e to the u. I guess we'll just write it this way. So it's e to the u, and then the 1 over x squared dx is negative du. And so now we just get negative integral of e to the u du. And we all know that one. That's e to the u. Don't forget there could be a constant there, because when you take a derivative, the derivative of a constant is 0. So there could be some constant there. And then we'll just substitute back in e to the 1 over x plus c, like so. How's that, Sandra?
Good, thank you.
Yeah, you're very welcome. So this is the type of example you should be able to do. This is the difficulty level that I want everyone to be able to do. So you can expect something like this on the test. This is kind of like, it's not easy, but this is like, remember we talked about like a C level question. I want a C student to be able to do this. So if you want to get at least a C, this is the kind of problem I want you to be able to do for the final. All right, so we are just taking requests. Either we could go from the study guide from chapter 5, or we're just taking homework questions too.
Can we please do 29?
Yeah. All right. All right. So this one, you notice you have 2 functions here. You have the sine of x and you have the cosine squared of x. You really have 2 options. You could do u equals sine of x or u equals cosine of x. Now to me, it feels like sine of x would work well because then du is cosine of x dx. The problem is you have cosine squared. So there'd be an extra cosine of x in there somehow. So let's try the other one. If u is cosine of x, then du will be negative sine of x dx. Well, that's almost what we have, sine of x dx. So what if we multiply both sides by -1 and say, well, negative du will be sine of x dx. If I restructure this, I could write this as cosine squared x times sine of x dx. And so actually it's the second one that ends up working here, because this becomes u squared times negative du, which should be negative integral of u squared du, which would be negative u cubed over 3 plus c, which would be negative 1/3, and then u was cosine cubed x plus c. All right, is that one okay, Sandra?
Yep. Mm-hmm.
All right. Good. Good questions. These are good ones. Any additional requests? 25, Haley said. Ooh, this one is, I give you a hint here. Well, that takes all the fun away. I'm not going to give you any hints. You don't get hints in life. Well, so sometimes I do give hints. I should take that back. If you look back on old exams, I've given hints before. But I probably will not be giving them for this particular type of problem. But let's try this u. So u equals x cubed. Du will be 3x squared dx. So we have x squared dx, so we'll just divide by 3. So 1/3 du will be x squared dx. So that's good. So we have 1/3 du is x squared dx, and then we have the square root of 1 minus, let's see, x to the 6th. Well, x to the 6th is x cubed squared. So that'll be u squared. I'm going to pull that 1/3 out in front. It's just a constant multiple. So I get 1/3 times the integral of du over the square root of 1 minus u squared. And now, this is not one we've done a lot, but this is one you're going to want to have written down. Does anyone know what this one is?
Sine inverse?
Yes, it's the inverse sine. I think your book uses the -1 notation, if I recall. Some books use the arc, A-R-C, arc sine. I think I've used that pretty often too. I've seen both. They're equivalent. And so then this would be 1/3 inverse sine of x cubed plus c. Does that clarify that one, Haley?
Yes, thank you.
Yeah, you're welcome. So that one's a little bit harder because the function isn't familiar. So you'd have to have that, you might remember it. Like, I mean, I remember it because I've done a bunch of arc sine problems. But you might not remember that one. It's not as common. So it's a little bit harder because you'd have to know, like, you'd want to recognize, like, ooh, this looks familiar. Let me go look it up because I've got it written down on my sheet. Some of these, this is what Albert was saying, some of these key antiderivative formulas, that arc sine one is, you want to have all of those, you want to have all 3 of those written down on your sheet. All right, good. Any other questions? We're working on homework right now, if anybody has any additional homework questions. All right, 53. Ooh. This one's easier than it looks. It looks hard. The key on this one is that when you have a sum, you can split it up. And so the key to this one is this will be equal to the integral of sine of x dx plus the integral of cosine of 3x dx. That's the key on this one. The first one, I feel like even now, I still will like, well, I know it's cosine, but do I have the right sign here? Derivative of cosine is negative sine. Nope, I need a negative in front there. I feel like even now I always do it that way. So it should be negative sine. The other one though, we have to do a little work. So, I mean, I don't know. Since you are just learning these, you probably need to do some work. I can tell you what this one is, and some of my Calc 3 students can as well, because we do a lot of these, and there's a real pattern to it. But we'll do a U substitution for that one. U is 3x, du is 3 dx. We don't have a 3. All we have is a dx. So we'll divide by 3, 1/3 du equals dx. This becomes 1/3 cosine of u du. Which will be 1/3 sine of u plus c. And then u is 3x. So the key on that one is you can't do the u substitution as written because you can't do the u with the sine of x. If it was a sine of 3x, you could. But because it's a sine of x, you can't do the u with it. And so you have to separate them and do the two functions separately. Right. Good, that one, Haley?
Yes.
Mm-hmm. All right. Any additional requests? These are good ones. Okay, I have a blank copy of the study guide up. I do have the completed one I put up already. I put up a completed study guide, but I don't know if anybody here right now has any particular questions that you wanted to go over and see worked out from the study guide that's posted here in D2L. Study guide. So any kind of pretending we're prepping for just a chapter 5 test. Any additional chapter 5 questions or a type of example you wanted to look at?
I don't have a particular problem in mind, but can we do another example where you change the bounds?
Yep, sounds good. Well, those are pretty easy to make up. So let's just make up another one. Let's see, what's the type of function we haven't done? We haven't done one that involves a natural log. So if you recall, here's how I would make up these problems. Remember, natural log is 1 over x dx becomes the natural log of the absolute value of x plus c. So I'm going to try to think of something where there's the dx in the numerator and the x in the denominator. Ooh, let's make a really hard one. Okay, this may go horribly wrong, but I think this will work. No, it's 0 to 1. Yeah, 0 to 1. Let's give it a go. What could go wrong? What's the worst thing that could happen? Okay. This one, the reason why this one is hard, in my opinion, is it's harder to recognize the U here on this particular one. So in my opinion, I think that makes this one a little bit harder. The more of these you've done, you might recall that the derivative of the inverse tangent of x is 1 over 1 plus x squared. And you'll notice, oh, there's a 1 over 1 plus x squared in there. So we're going to let u be the tangent inverse of x. And du, so it's harder to recognize it, but watch this. When I do the du, That's 1 over 1 plus x squared dx. It's perfectly in there. So it might be harder to recognize it in the first place, but the substitution is super clean. It's a really clean substitution. Okay, now here's the change of bounds. We need to do u, because we've got this pretty much set up. This is du over u. So the u is tangent inverse of x, and then 1 over 1 plus x squared dx is du. So that's done. But now we have the change of bounds. So I need to evaluate u at 0 as tangent inverse of 0. So that's the angle whose tangent is 0. This means tangent of what equals 0. Now, I guess I'm kind of making it, you could just use your calculator, but what's the fun in that? So you know this. What's it? What angle's tangent is 0? The angle between negative pi over 2 and pi over 2.
Would be pi
0.
over 2.
It would be 0. It would be 0. Pi over 2, the tangent is undefined. It's undefined over there. Sometimes I think of the graph of tangent of x. And it's, if you graph x equals pi over 2, that's the asymptote there. That's the asymptote. So it's 0 at 0. Tangent of 0 is 0, and tangent of pi over 2 is undefined. There's a vertical asymptote there at pi over 2. But you can use your calculator. You should be able to do tangent inverse, like I could do that in Desmos. Tangent inverse of 0, and it'll give me 0 also. So, whoops. So you have some technology tools at your disposal, but it is important to know why it's valuable to know why they're true. U at 1 will be tangent inverse of 1. So that's looking for tangent of what is 1. In fact, I can graph that here. Y equals 1. And that's this guy right here. Do you see? Pi over 4. Because sine and cosine are equal at pi over 4. And tangent is sine over cosine. So that one is pi over 4. So now we're integrating from 0. Oh no, I was afraid of this. This is not going to work. You'll see. You'll see. We need to change the problem a little bit. God, so close. Okay, so I did this problem to get a natural log because we hadn't done any yet today that were natural logs. So this is why I always have to test my exams when I make them to make sure that every problem is doable. So this is natural log absolute value of u from 0 to pi over 4. And that's the natural log of pi over 4 minus the natural log of 0. Oops. What's the problem here?
ln of 0.
Eek. Not defined. Not defined. So we could change the problem if you want. We're done. You know, we've done this isn't the process that Allie was worried about. She was worried about the substitution process. But if we wanted to, we could just change that lower bound to not be 0, to be like, what's a tangent that you know? Tangent of pi over 6? Tangent of pi over 6? That's sine of, well, you can do unit circle, right? That's 1, 2, square root of 3. So it's square root of 3 over 3. So if we had done square root of 3 over 3 to 1, then this would be u at square root of 3 over 3 would be tangent inverse of square root of 3 over 3, which would be pi over 6. And then we would just, then we're good. We could even do properties of logs and go further there if you wanted. It's not super important, but it like bothers me to leave it. Do you remember the properties of logs when they're subtracted? You could combine them. Anyone remember? Natural log of A minus natural log of B. That's the natural log of A divided by B, properties of logs. So I could write this as natural log of pi over 4 divided by pi over 6. And so you actually get the natural log of 3/2. I'll let you simplify that on your own. Not a big deal. And again, not the point of what Ali was asking about. She was asking about changing the bounds. So that was the important part of this process. Just to reflect back on that, the key there is after you do your U-substitution, you simply evaluate the U at the lower bound and the upper bound. That's how you change the bounds of the new integral. Do you want to do another one, Ali?
That's okay. I think I got it.
Okay, good. Any additional chapter 5 requests, either a topic like Ali was saying, or if you want me, like I said, I have the study guide up. Any additional chapter 5 requests? Okay, seems pretty quiet today. What we have planned, we still have a few minutes left today. We could do some more review of some older things if you would like. And what we have planned for our schedule, we just have one more meeting tomorrow. And tomorrow is going to be entirely just whatever you want to talk about. I have lots of materials I've posted, and I can't like prepare a review. It's an hour and 5 minutes. We can't review 3 months of material. So it needs to be stuff that you have looked at and you're like, you know what, I want to review this. So you can email me ahead of time. You can post in the chat during class. You can just bring it up. But it's going to be focused tomorrow on things that you want to review. You can look at old exams and use those. You can go to the final exam materials. You see I have all the old exams and old study guides. So you could bring up that stuff. You could bring up, you know, whatever you want. But it's going to be, tomorrow's going to be focused on questions that you have. So we do have a few minutes today. Is there anything that you've been studying that you've been thinking of and you wanted to ask about that you want to bring up for the last few minutes today? Chantel, did you have something? Looks like you were maybe looking for something, or?
Yeah, there was an old question on a Unit 3 test, and now I can't find my Unit 3 test.
All right, let me pull it up. I've got them all here.
Professor K, I have a quick question.
Go ahead, go ahead.
Moving forward into the later calculus classes, now that we know how to find the definite integral with just doing the area, is it still useful to know about Raymond's sum and those other things?
That's a really good question. So yes, it's a really good question. It is super useful to know kind of how they're built, but not how to actually find the Riemann sum. So what I mean by that is, even in Calc 3 now, we still are doing the sum of stuff. Oh, that means adding them all up, that's an integral from A to B of something. So that idea of a sum of something, which is the Riemann sum, equaling a definite integral, super, super important. It's super valuable in Calc 2 and Calc 3. I'm trying to think of differential equations. It's somewhat important there. But that idea of you make like for example, here's what we were just doing in Calc 3. Imagine 3 dimensions. You have some surface in 3 dimensions. you find the area of some little representative piece on the surface, and then you add them all up, which would be like an integral. It's actually a double integral because you have to add them up this way first and then add them all up this way. But it's we still look at representative pieces all the time. What's this representative piece, and then add them all up. So that more conceptual is the value, not the finding the limit as n goes to infinity. We don't do that. But it's just the concept of adding them up. Does that make sense?
Yes.
Mm-hmm. Chantel, I can scroll through here, or did you find yours?
No, it was like one of the final problems on the exam. It wasn't the Newton's method.
Okay, and then we have this this differential idea.
Yeah.
That's the last problem. So differentials,
I think maybe
Newton's
it was
method.
10.
And so then there's this the coronavirus one about the rate of change. Mm-hmm. So a lot of this is like, what is happening? Like, what's the question asking? So whenever I see a function, well, I was going to try to write on it. Actually, I can. Hold on. Let me see. Can I get the whole thing on here? No. So we're trying to find a function representing how fast the number of cases will increase, and then find that rate of change 42 days after March 1st. So I'm going to click annotate here. Then it will let me, I think it'll let me write over the top.
Okay.
Okay. So this right here, I want to know, what does this function represent? And it's the number of cases. So that's super important. That's that's the number of cases.
Okay, here we go.
I'm just going to mute you, so don't worry about it. Just pay attention when you can. So this is the number of cases. I want to know how fast the number of cases is increasing. Well, the rate of increase will be n prime of t. That's that focus on what does the derivative mean? It's a rate of change. And so here, it's the rate of change of this function, which is an exponential function. So it's 328. And the rate of change of an exponential function base e is just that same function back at you, e to the 0.212t. But then we have to do a chain rule. So we have to multiply by the derivative of the exponent. So we have to multiply in this case by 0.212. Sorry, I planned my spacing out poorly there. So the key there is, again, the rate of change is the derivative. So that's what we're looking for here. And then I'm just getting out my calculator. 328 times 0.212, 69.536 e to the 0.212 t. And so what that represents, what that derivative represents, that represents how fast the number of cases is increasing. It's a rate of change. So it's all, this question is all about, well, I mean, there's a derivative of an exponential function here, but it's all about, what does derivative mean? It's a rate of change. And then I'm going to scroll down here, and it's going to be weird because all the print is still going to be there. Well, I can stop annotating. All right. And then it says they can't continue spreading exponentially, which is true. So should the trend continue at the same rate, how fast will the number of cases be increasing on April 12th, which is 42 days after March 1st? State your answer with appropriate units. So the key for that one is you just want to find n prime at 42, which is 69.536 e to the 0.212 times 42, whatever that ends up being. And then for units, n is number of cases, t is in days, so n prime of t is cases per day. It's a rate of change, cases per day. And that would be the units here. So how's that one, Chantel? Does that?
Yeah, no, I appreciate it. Thanks.
Yeah, no problem. All right, this is our time for today. We are up for today. Tomorrow will be our last class meeting where we will meet, I almost said in person, but virtually. We will have our last live class. And then immediately after class, I'm gonna have the exam program to automatically pop up right after class. So then kind of questions are done then because the exam is out. And this is the final exam. So no messing around. I'll probably put it like 10:45, something like that, right? So it's like right after class. So once it's out, questions are done. So if you have questions you want to ask, email me now during class tomorrow, but then once class is over, that'll be it. And the exam will be posted, but you have all day tomorrow and all day Wednesday to work on it. So and then it'll be due to the Dropbox by the end of the day on Wednesday. Okay, any last questions before we end the class today? All right. I may not be super responsive this afternoon because I actually am meeting with every single one of my classes, including the additional class I picked up to substitute for someone else who got sick and had to leave right when we went remotely. So I have class from 1 until 6 this afternoon. So I may not be super responsive then. So if you email me, I might not be until tonight when I email you back. All right. Thanks, everybody. I will see you virtually tomorrow at same time, 9:30. Yeah, Allie, before we go.
If you were going to stick around after class or if I should just email you.
I can.
Okay.
Yeah. All right. Clear all the drawings there. Did you want to meet privately?
Yes.
Okay. All right. So I'm going to end the class then, and then I will do the office hours. So I'm going to email you a link, Allie, okay?
Okay.
All right. So check your student email, okay? All right. Bye, everybody.